I'll begin. Dear Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. I just pray you help us to use this time wisely and also to enjoy the weekend. In my prayer, Lord Jesus. Amen. All right, so let me get into it here. First of all, turn your homework. Pass it over, please. Thank you. So last time I described for you, briefly, the theory of vectors in the plane, how to add them, how to scalar multiply them. I even told you something about the dot product, which you probably don't need. I mentioned to you the properties of calculus of paths. The properties of calculus of paths, basically, you got these wonderful properties, which I haven't really done much with, and I might not. Just telling you for your informational purposes, and because it would seem like a shame not to mention them. I suppose I haven't really used those yet, and maybe I won't. But anyway, there they are. And then I mentioned to you, if we have a path, a pair of functions of time, x of t and y of t, so as t varies, it ranges over some curve, all right? And this is a parameterization of the curve. That's what a path is. Then you can define, and of course, in the case that it's actually describing a physical thing, an actual material object, you can think of r of t actually being the position at time t, right? It's actually like the position of some car or plane or whatever you want to study. Thank you, sir. And then, of course, on the other hand, we can do calculus. We can differentiate the path. And that's just meaning that we differentiate each component separately, right? So like v is just dx dt comma dy dt. It gives me a vector, actually, that points in the direction in which the path is changing. I don't have too much to say about that at the moment. Maybe I should, I don't know. But if we calculate the magnitude of the velocity, then that gives us what's called the speed. The speed is actually the square root of dx dt squared plus dy dt squared. And you can argue, you can show for smooth curves that the speed is actually the infinitesimal change in arc length with respect to the instantaneous change in time. In other words, you have ds as the infinitesimal arc length subtended in a time dt along the path. So then if you know that, you can integrate it, right? And so the integral of ds dt over some time range gives you the net change in s, which we just call s. And so that gives me the arc length of a path, smooth path, which goes from A to B with parametric functions x and y. Here's a heuristic proof of this infinitesimal claim. Let me just walk you through like a little picture, all right? So here's the idea up here. I've got some, well, I'll let you guys catch up. I want to make sure everybody's looking at it. So once everybody's caught up with me, I'll point at the picture. You guys with me? Mostly? Okay. So here's a curve, right? Right here. Right? And I'm supposing I have some parameterization of the curve, all right? Some path which follows the curve, r of t. And what I want to do is just study this point versus that point. Like there's some little change in position vector. It's called the displacement in physics, a little delta r, which connects r of t and r of t plus delta t. Right, so a little change in time, a given time, all right? So I'm comparing these two particular points on the path. So the change in r I can get by calculating the difference, right, of r of t plus delta t and r of t. If you don't see that, if you haven't studied vectors enough, let me kind of try to explain it to you. So I mentioned to you guys last time the way we add vectors is tip to tail, right? If you want to take vector A plus vector B, put them one after the other, and then the resultant is what you get from going from the start of A to where A plus B ends up. So here, if you look at this one, I have the blue vector, right, plus the purple vector, that should be the same as the pink vector. See that? This tip to tail with the purple vector gives me the same displacement from the origin, this pink vector. Do you guys see that? Blue plus purple is the same as pink. That's how vector addition works. So what that tells me, right, is just what? R of t plus delta r is equal to r of t plus delta t. Right? This is the pink vector again. And of course, once you have this, it's easy to solve for delta r. So there you go. Delta r is r of t plus delta t minus r of t. Okay? Fine. Now what you do, divide by delta t. Divide both sides by delta t. That gives me this. And then if you take the limit as delta t goes to 0, well, the limit of the change in r over the change in t, guess what it is? It's exactly dr dt. I haven't proved that, but it's true. And that is the velocity. So what we have then, approximately, is that the velocity, so here, if we set the velocity equal to the average velocity, which is delta r over delta t like this, that gives me, and then I can multiply both sides by delta t, that gives me v times delta t is equal to delta r, right? Now, on the left-hand side, the length of this vector is just the speed times delta t, because delta t is just a scalar. So if you take a vector times a scalar, its length is just the length of the vector times a scalar. I'm assuming delta t is positive. And then on the other side, we have the length of delta r. Well, to a very good approximation, the length of delta r is what? That's exactly what we mean by arc length, right? So the little green curvy line has almost the same length as the purple line segment, right? If it's smooth enough, right? And so this is an approximation, but basically if you look at the limit as delta t goes to 0, we get that v is equal to ds dt. So the speed is connected to the arc length in this way. And again, if you want to get the net arc length, you just integrate ds dt with respect to t. So the integral of the speed over the appropriate time domain gives me the arc length. That's good? Well, it's not quite good. I should replace this with a more rigorous argument. And I'll probably do that in a few minutes, but I want to do an example first, or two, or three. And I also need to talk a little bit more about how to parametrize curves, so we'll keep working on that. All right. Here's an example. You have r of t is 3 cosine t and 2 sine t, right? So up here is what's given. And the question is basically describe this. Describe this path. What is it? So the first thing I would do, right, is I might just plug in some points. Plug in like t equals to 0, plug in t equals to pi over 2, plug in t equals to pi, plug in t equals to 3 pi over 2. When I do that, I get 3, 0. I get 0, 2. I get minus 3, 0. I get 0, minus 2. See, because, cosine of 0 is 1, cosine of pi is minus 1, sine of pi over 2 is 1, sine of minus pi over 2 is minus 1. If you know those things, you didn't just waste a minute needlessly plugging numbers into your calculator. If you don't know those things, it artificially inflates the time it takes to do this problem. It's really important to know basic angles for sine and cosine for problems like this. You pay a heavy penalty by not knowing your trigonometry here, believe it or not. Anyway, enough about stupid test-taking strategies. So you keep plugging in points, eventually you get something that looks more and more like an ellipse, right? And then you're like, okay, I think this is an ellipse. Let's check it out. Is it actually an ellipse? Well, I know that 1 is equal to cosine squared plus sine squared, right? I need to convert this to x and y to find its Cartesian equation. So I can replace cosine with, I can just basically multiply and divide by 9. So that's like 3 cosine t squared over 9. That's the same as cosine squared, right? And this is 2 sine t squared over 2 squared. Why am I doing that? It's because I'm given x is equal to 3 cosine t. I'm given y is equal to 2 sine t. I'm trying to change this to x. I'm trying to change that to y, so this is how I personally saw to do it. Maybe you guys would just solve for cosine and plug it in, solve for sine, plug it in. That's also fine. I just sometimes do algebra a weird way, right? So it's up to you. I mean, anyway, the point is you can solve for cosine and sine, plug it in here, and you'll get that. Agree? So this is, in fact, a path which covers this ellipse. So if we take cosine and sine and multiply by numbers which aren't matching, we get ellipses. Bottom line. As long as those are positive numbers. I guess if they're negative numbers, we probably still get an ellipse, right? Yeah. All right. Great. So that's a parametrized curve. We could have studied it last class. But the new thing that we have to do now is to calculate its arc length, right? What's its arc length? So we have to integrate from 0 to 2 pi the speed. The speed is the square root of dx dt squared plus dy dt squared. All right. That's the square root of 9 sine squared t plus 4 cosine squared t. In a hope for something magical to happen, I eliminate the cosine squared. It doesn't help. Okay, this integral is a good example of one of those integrals where we have made up a name for the function, which is the antiderivative of this integral. If you plug this into Wolfram Alpha or Mathematic or something, it'll come back at you with like, this is an elliptical function of the blah 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 kind at minus 5/4 or some such nonsense. Which is just a way of saying we've made up a function to tabulate the values of these integrals. Great. Anyway, so numerically, this integral works out to about 15.87. That's kind of usually what happens. You're not going to exactly calculate most arc length integrals, is my point. Because it's the integral of a square root of stuff. That's a notoriously difficult problem to solve in general, right? But there are textbook examples which will have nice things happen, right? For example, this one. So I can do this one, I'm pretty sure. This will make us feel better. Suppose you look at x equals to r cosine t, y equals to r sine t, r is positive. This is a parameterization of a circle. Right? So what? Let's calculate its arc length. So what do we do? I'm going to take a slightly different approach here. I'm going to actually write the path. The path is what? R of t is equal to what? R cosine t, r sine t. What's the velocity? Derivative, right? Differentiate both. What's the length of the velocity? That's the speed. Which is what?
Some squares of the derivatives.
But what is that? R. We have a winner. Yes, sine squared plus cosine squared is 1. The square root of r squared is just r. We're assuming r is positive. All right? Now, this is also equal to what? This is equal to ds dt. The infinitesimal change in arc length with respect to the infinitesimal change in time. To find the net arc length, I merely integrate with respect to time. So s is the integral from 0 to 2 pi of ds dt, right? But just to get to the point, that's the integral from 0 to 2 pi of r dt, which of course is 2 pi r. The arc length of a circle is 2 pi r. I hope this is not surprising to you. But isn't it nice to actually calculate it? What's that? Oh, circumference. Yeah. But yes, I mean, admittedly, if you just give me a random curve and try to calculate the arc length, odds are very good that I can't do that integral in closed form. That is true. All right. So I'm bouncing back and forth between a few different tasks in here because if I do any one of these tasks for too long, you stop paying attention. And there are also things that you need to absorb over a period of different days. So like my lecture style in this part of the course is a little bit like that game they play on The Price is Right with they drop the thing in it and then it like goes this way, then it goes that way, then it goes this. Yeah, the Pingo. Yeah, it's like that. That's my current lecture style. What's that? I think it's hard. Yeah. I know. Okay. So anyway, what I'm doing then at the moment is I'm kind of going back to last class for just a couple minutes and asking you these two questions. And then I'm going to come back to arc length again, okay? So you guys tell me, if I want to parameterize an ellipse, what are the parametric equations for an ellipse? Now, I showed you an example over here, a specific case. Now I'm just generalizing. For A and B, what are the parametric equations? X equals what? Y equals what? I mean, I'm choosing that. I'll start us out. A cosine t. What's that? B sine t. We have a winner. Yes. How did you know that? So you visualized trying to find formulas that when I plug in here it works, basically? Yeah. That is also how I do it. But there's no algorithm, generally speaking. So you can check, right? That x squared over a squared plus y squared over b squared equals to what? Cosine squared t plus sine squared t, which is 1. So, in fact, those parametric formulas work. If I was so foolish as to try to calculate the arc length here, what would it be? So dx dt is what? It's a sine t minus a sine t, right? So you'd have a squared sine squared t plus, and then the derivative of that would be b cosine t, so b squared cosine squared t, right? dt, and that just generally is unpleasant. When a is equal to b is equal to r, we can do it. Otherwise, that happens. All right. Oh, I suppose I'm only, fine. I guess I should say just a little bit more about this example. I don't know. Should I? Maybe I should. No, I'll stop myself. There's always more to say about the geometry of curves, guys. Always more to say. But most of those things should be said in Calculus 3, so I'll behave. Parameterize this curve. X squared over a squared minus y squared over b squared equals to 1. A cosh t. Do we agree with Mr. On? I think we do, because if we try x squared over a squared minus y squared over b squared, what do we get? The a's cancel, right? We get a squared cosh squared divided by a squared, and b squared sinh squared divided by b squared. The a squared and the b squareds cancel, and you've got yourself a cosh squared minus sinh squared. Otherwise known as 1. So in fact, yes, those parametric formulas do at least fall in that Cartesian equation. Now I have x greater than or equal to a. What about that? By the way, what range of t should I do this for? I'm going to tell you we should do this for t in the reals. So how do we deal with this? How do we check ourselves on that? We know hyperbolic cosine. We know how it works, right? What's the deal with hyperbolic cosine? Cosh of t is greater than or equal to 1, right? That's its structure. It's like a parabola that opens up with a y-intercept of 1, except it's exponential on both sides. Remember, back when we graphed it? One of the fundamental things we noticed about it, it's at its smallest 1. It's 1 at 0, and everywhere else it's larger. Okay, so what? Multiply by a, right? We're assuming what? I should have told you guys. In both of these examples, what do I assume? And what does the book usually assume as well, whether he says it or not? A and B are what? Positive. Yes, and they're constants also. You guys always ask me questions about that at some point, and it catches me off guard. I'm like, yes. Why wouldn't you make them constants? Yes, they're constants. I haven't done anything that ugly in class. Why would you do that? The problems are hard enough without doing that. Why? Why? Anyway. And then, in later classes, once we actually get to abstract mathematics, when I actually want students to be abstract, like you guys are being there, then all of a sudden, you guys make it unabstract, and you just assume it's a special case. It's very, very frustrating. Anyway, not you guys, of course. You guys are not going to be like that when you get to the higher classes. All right, x greater than or equal to a is what we have. Oh, hey, but that's what we want. In other words, it's just like the example I worked the last class where we had the right half of the hyperbola, right? But now I've done it for arbitrary a and b. Okay? Oh, I'm kind of afraid to calculate the arc length here. I don't think I'm going to be able to calculate it either. What would the arc length be if I was just to what's the integral solution to the arc length? S would be the integral. Ooh. Well, we know this. I mean, this, come on. I mean, it's not even worth writing in some sense, because you already know it diverges, right? What's the arc length of the hyperbola? So the best we could do would be to like calculate the arc length of like a part of it, right? So here's something you could do. You could calculate the arc length to time t based at 0. So you could do like integral from 0 to t, and then like ds d tau. That would give you like the integral from 0 to t of the square root. Let's see, dx dt squared here is what? Or d tau squared, I should say. Yeah, like a squared sinh squared tau plus b squared cosh squared tau d tau. I've introduced a tau instead of a t because I'm treating t as a constant here. I'm trying to calculate what's the arc length starting from 0 out here to like r of t, right? So this would be s of t. So this would be what's called the arc length function, based at 0. Yes, sir?
Don't you have the same equation that you found for when you did the tau squared t minus sinh squared t?
Because this is the arc length, which is the integral of the speed. The speed is dx d tau squared plus dy d tau squared here. So like x is equal to this, so if I differentiate, I get a sinh. If I differentiate this, I get b cosh. So then that gives me a sinh squared plus b cosh squared. Going back again to the definition of speed as being the square root of the sums of the x component squared plus the y component squared for the velocity. What would the arc length function be over here if you did s of t? Integral from 0 to t of ds d tau d tau. What would it be? What do you get? Just RT, right? There's an interesting thing you can do. You can take the curve you're given, right? And you can rewrite the curve. You can reparameterize the curve in terms of arc length if you want. So what I have here is RT is equal to S. So what's that say? That says T is equal to what? S divided by R, right? So if you define a new parameterization, let's say R2 of S, which is equal to, let's say, R cosine of S over R, R sine, see what I'm doing? I just plugged in, I replaced T with its formula in terms of S. What's the velocity of this thing? When we differentiate with respect to S, what happens? We pull out a 1 over R by the chain rule, right? It cancels the R that's there. What are we left with? It's like minus sine, right? And cosine, right? Differentiating, do you guys see that? So what's the speed of the second? The speed of the second one is what? What's the length of this vector? Square root of sine squared of S over R plus cosine squared of S over R. In other words, 1. The length of that vector is 1. Does that make sense? What is the length of the vector, generally speaking? ds over dt, right? But what is t here? It's s, isn't it? Not an accident. So if you reparameterize a curve with respect to arc length, it gives it unit speed. It gives it speed 1. You can easily prove that from fundamental theorem of calculus. Check it out. If I calculate ddt of the integral, say from 0 to t, of v of, see here, try that again. Oh, man. Oh, a lot of energy here all of a sudden. I'm not sure this is the right notation. V of tau d tau, let's say. All right. What's that give you? Uh-huh. V of tau, yeah, V of t, right? This is what we call S of t, right? So therefore what we have is what? ds dt is equal to the speed at time t. Right? So in the case you take t equals to s, that reduces to 1. Make sense? I mean, I just showed you it happens. So I don't know. So the arc length parameters, I talked a lot about the fact that we could choose all sorts of different, you guys noticed that we could choose all sorts of different parameterizations for a given curve, right? We have tons of choices. However, this choice, this arc length parameterization, is kind of different, right? There's something geometric about this which is intrinsic to the curve. So this stands out as one choice of parameterization, which maybe there's not so much ambiguity in, right? There is still one ambiguity in this, right? Which is where you base the arc length. I chose 0, but you could start, you can calculate the length of a curve starting at any different point, right? If you pick up, if it's not a curve with endpoints, if it's like a curve that goes on and on, you could start the arc length at different points on the curve, right? So the arc length function is only defined up to some sort of like translation of arc length or something. But it's nearly unique. Nearly. Okay. Oh, I guess one of the things I should show you before I forget is the arc length formula for a graph. What's that look like? How do you calculate the arc length of a graph? There's kind of a special formula in that case, right? What if you have y equals f of x for a less than or equal to x, less than or equal to b? In other words, it's something like this, right? Kind of our old happy place. This is what's the length of that curve? Well, what you can do is you just use the standard parameterization. Like r of t is what? What's the path that covers that? Talked about this a little bit last time. It's what? It's t, f of t, right? In other words, x is equal to t, y is equal to f of t, right? So then what do you have? You've got dx dt is what? Well, let me just get to the point. The arc length then is the integral from a to b of the square root of dt dt squared plus what? df dt squared dt, right? Which is what? That's the integral from a to b of what? Square root? That's what? 1 plus df dt quantity squared dt. And so there's the standard formula for the arc length of a graph. I guess that's not the standard formula. Usually, what would they do? They just put t equals to x and do what? They write this instead. That's the same thing with the understanding that y equals f of x, right? And t equals x. Same formula. This is just a special case of the more general parametric arc length formula, though, okay? The parametric view is general, and that's what we should take as primary. Any questions? I probably can. You probably can think of some. Can you guys think of a function that we'll be able to calculate the arc length explicitly for? Can you guys think of some function that when we put it in here, we're going to get an example we can actually calculate the arc length of? I'm asking you an inverse question. We don't usually ask those of students, do we? My question is, give me an example for which you can calculate the arc length and not a circle. A graph of some sort. If this is, let's see here, we know what? 1 plus, how does it go? 1 plus tangent squared equals secant squared. So if I can make this come out to tangent, we'd be good. What do you differentiate and get a tangent? The integral of tangent, right? Integral of tangent's what? What's that? Integral of tangent is not secant squared. Integral of secant squared is tangent. Other way around. It's not secant tangent either. You guys are killing me. Yes, log. Natural log of the secant of x, I think, is the 1. dy dx is what? Yeah, 1 over secant x, and then we got what? Sec x, tangent x, right? We have a winner, yes. So while this is scary, if you just see it, calculate the arc length of the natural log of secant of x from 0 to 1. Looks kind of scary, but actually this is a benign problem because the arc length, right, will be the integral from 0 to 1 of the square root of 1 plus dy dx squared, because this is a graph. And so that's not too bad. It's integral from 0 to 1 of the square root of 1 plus tangent squared, which is what? That's secant squared, right? So the point is that's actually the integral from 0 to 1 of secant x dx, which we remember is the natural log of the absolute value of the secant x plus tangent x. Remember that because we don't want to do the integral again. Unless I was to tell you to derive the integral of secant. Yes, this is something I have said that you are allowed to memorize. Anyway, so there it is. And then what is that? Well, that's natural log of the absolute value of secant 0, secant 1, right? Plus the tangent of 1, minus the natural log of the absolute value of secant of 0, plus tangent of 0, but that's 1, and this is 0. So there you go. That's the arc length. And I stand by my assertion that this is a nice arc length example. You might not feel like that, but in the world of arc length, actual arc length calculations, that's not too bad. All right. What does this look like for a curve which is described in polar coordinates? How do you calculate arc length in polar coordinates? What does that even mean? Let me state the problem precisely. Suppose you're given a curve where r is a function of theta over some range of theta. Given r is equal to r of theta for some, say, theta 1 less than or equal to theta less than or equal to theta 2, find the arc length. What are we going to do? We must produce the path, right? We should just produce the path which gives you this curve. What path gives you this curve? Instead of saying r of theta, let me just call this something else so it's easier to see what's going on. Let's call this g of theta for the purposes of this discussion, all right? So what's the path? Say r of t. Basically, what we want, right, is to use theta. Our idea, our concept, is what? It's just theta is equal to the parameter, you know? And so we just use polar coordinates, which is what? Like, you know, r cosine theta, r sine theta, right? But what that actually means is what? Here r is equal to g of theta, which is g of t, right? So I actually have g of t, cosine t, g of t, sine t, right? This is the path written in polar coordinates. I mean, it's the path which comes from polar coordinates, I should say. And then what do you got to do to calculate? You need to calculate the speed of this, right? So this is x. This is y. So what's dx dt? What's dy dt? Aw, man. We got product rule to deal with here, don't we? So this is what? This is g prime, or dg dt, cos t, minus g sine t. And that one gives us dg dt sine t plus g cos t. Square those, what do you get? What's dx dt squared? It's dg dt squared cosine squared t minus 2g dg dt sine t cosine t plus g squared sine squared square y, what do you get? Yeah, kind of the same thing. But the difference is what? Sine is replaced with cosine, basically, right? And also that plus changes to a what? I mean, the minus changes to a plus, I should say. So you get 2g dg dt cosine t sine t, I suppose, plus g squared cosine squared t. So everything's almost the same. Which is fantastic, because that means if we add these, what happens? We get dx dt squared, right? Plus dy dt squared equals to what? Right, dg dt squared plus what? Plus g squared, yeah. This is a precious relation. It's more fun to look at if you say g is equal to r and then multiply by dt squared, formally speaking. What this gives us is that dx squared plus dy squared is equal to what? It's equal to dr squared plus r squared. I should set, I got dt squared, but I want to write d theta squared since we have t equals to theta here. I mean, geometrically, this is what's going on. So you think about it, you got like this little, little ds here. You can either look at it in terms of, dx and dy, right? Or you can look at it in terms of like, or you can look at it in terms of like this, like a dr, and then over here an r d theta. So these are just two different ways of writing the infinitesimal arc length squared, either in terms of x and y or r and theta. Of course, I haven't used a heuristic like that. I've just derived it from the calculus of paths down here and then seen the heuristic from that. Anyway, long story short, what's the formula that we have just found? To find the arc length for a parametric curve, then we just have to integrate from theta 1 to theta 2, right? It's the square root of what? dg d theta, let's say, I'm just write it out again. It's basically r squared of theta plus dr d theta squared d theta. That's, where r is a function of theta. So that's the converting back, getting rid of my g and going back to r at the end. That's the arc length for a polar curve, and that's why that's that formula. Of course, I could just drop this formula on you from the sky and say work with it. And pragmatically speaking, that's what you can do at this point. But I want you to understand it's just part of this natural, larger discussion of the arc length of paths, just like this formula over here. Now, I guess we could do something foolish, like try to calculate the arc length of that logarithmic, that spiral we looked at. What was it? this thing. What was that? That was r equals to theta, right? What if we wanted to calculate the arc length of one full spiral? We would have to calculate the integral from 0 to 2 pi of the square root of what? R is equal to theta in this case. So that first term is theta squared. And dr d theta is 1. Right? So theta squared plus 1. Hey! I can do that one, but not in 2 minutes without hurrying. You make a hyperbolic substitution, and so forth and so on, right? We learned how to integrate something squared plus 1 square rooted, or you can make a trig substitution to do it. So I don't want to do that right now. I don't want to cram that in the last minute, but all right. So I hope I've convinced you that the concept of a path is something that is useful as an organizing principle, if nothing else. We've been able to talk about graphs of functions, about curves which are described by by polar coordinates, and just by generic paths, all in the same theoretical framework. Anyway, have a good weekend. I still owe you a more careful proof of the Arclength formula. When we go over that, we may yet understand why it is